So, in my today's topic, it is kinetics of complex reactions. Interpretation of velocity data of many reactions becomes very difficult due to the occurrence of several reactions which take place simultaneously along with the main reaction. So, the elucidation of the exact kinetic law requires carefully planned experiments to study the influence of products and reactants. Let's consider a few such reactions. Important reactions in this category are opposing reactions. Parallel reactions and consecutive reactions apart from the chain reactions. Details of mechanisms of these reactions will be discussed now. Some reactions may proceed. Now, we are studying about opposing reactions. Some reactions may proceed to a state of equilibrium and may not go to completion. The simplest case of this occurs when both the forward and reverse reactions are of first order, which can be represented as follows. A going to X, X returning back to A. Here, K1 and K2 are the rate constants in the forward and reverse reactions. Let the initial concentration of A be A. After a time t, X grams of A decomposes to form X. X grams of A decomposes to form X. So, the concentration of A at time t will be given as A minus X, and concentration of X at the same time is X. So, the rate of forward reaction is equal to K1 A minus X, since it is going forward. But rate of backward reaction will be equal to K2 and only X. So, the net rate of production X will be equal to dx by dt is equal to k1a minus x minus k2x. But we have to count it at equilibrium. So at equilibrium, dx by dt will be equal to 0 because the reaction has stopped at a particular place. Neither it is going ahead nor it is coming backwards. So it is at equilibrium, it is at 0. So now this whole equation will change dx by dt is equal to k1 a minus x minus k2x, which are now at equilibrium. So x equilibrium will be equal to 0. That is, Xe is the concentration at equilibrium. So now k1 a minus x e therefore will be equal to k2xe, or you can say k2 is equal to, when we shift the whole thing over here, k1 a minus x divided by xe. We have got the value of k2. Substitute this in this equation. So what we get now is dx by dt is equal to k1 a minus x minus k1 a minus x divided by xe into xe. Now what we get? That is equal to when we open the brackets, we get k1 a minus k1x minus k1a divided by xe into x plus k1x divided by xe into x. That will be equal to k1a minus k1x minus k1a divided by xe into x plus k1 into x. This is xe here. So it will be e here. This and this gets cancelled. So now what we have is equal to minus k1x plus k1x will get cancelled out. Now what we have is k1a minus k1a divided by xe into x. This is equal to k1 common, a common, 1 minus x divided by xe. Therefore, dx by dt is equal to k1a divided by xe into xe minus x. When we bring the similar terms together, dx by xe minus x is equal to k1a into dt divided by xe. Now on integrating, what we get is minus ln xe minus x is equal to k1a divided by xe into dt. Plus constant. T is equal to 0. X will be equal to 0. Therefore, this term becomes 0. Ln of xe is equal to whole term dt will be equal to 1. Therefore, we have ln of e is equal to constant. Substituting the value of integration constant, we have, when we substitute this value, what we have is minus ln of xe minus x is equal to k1a divided by xe into dt minus ln of xe. Open the brackets, minus ln of xe plus ln of x is equal to k1a divided by xe into dt minus ln of xe. Or similar terms together. Over here, that is plus ln of xe is equal to K1 A by Xc into dt. Now this is minus, this is plus, so Xc we can write it like this. Ln of Xc divided by Xc minus X is equal to K1A divided by Xc into T. Or we can say K1 is equal to Xc divided by AT into ln of Xc divided by Xc minus X. Our This is our kinetics. This is our opposite kinetics of complex reactions. Subunit opposing reactions. We have been able to find out this formula for any reaction going in equilibrium. For any reversible reaction going in equilibrium. We'll continue with this topic in our next class. That's it for today. Thanks for watching.